Thanks very much for inviting me to come talk. So I'm going to be talking about a paper that came out in December with Adam Brown, Frank Garabian, and Lenny Siskind. It's called The Python's Lunch, and it's based in large part on some earlier seminal work by de Saint-Exupéry. Okay. So yeah, I'm going to have sort of two parts to the talk. The first part is going to be not about the paper that came out in December. It's going to be a review of some arguments based on paper I put out in May and a load of other papers that have come out at the same time and since on how we can see, just sort of using semi-classical gravity, that information that falls in the black hole starts coming out at the so-called page time, and the entanglement entropy goes down, follows the page curve, and so on. And then in the second part of the talk, the main part, we'll be talking about how we can see from semi-classical gravity that information that fell in the black hole can't be reconstructed from the Hawking radiation. So I haven't gone completely schizophrenic. I'm not going to be entirely contradicting myself. There is an important difference between these two parts, which I didn't clarify, which is the first part's about what's possible in principle. From an information theoretical point of view, if you had infinite sort of computational power, what can you find out? And yeah, what you see is that Hawking radiation encodes the information from that point of view. But in the main part, I'm going to be talking about how we can try to see that reconstructing the information is an exponentially complex process. And there's going to be another important difference between the two parts. So the first part of the talk, I'm not going to get into these calculations, but it truly is based on precise calculations using a gravitational path integral. The second part of the talk is not. There's some calculations, certainly. There is some maths in there. But the actual calculations are not going to involve gravity. They're going to involve tensor networks. And then we're going to tell a story about how hopefully we think gravity may be analogous to this. Yep.
When you say it can be reconstructed or not, you mean from black holes that have not fully evaporated?
Yes, yes. I'm always going to be talking. Anything that involves black holes completely evaporating, you have this at the very end of the evaporation, they become Planckian in size. There'll be all sorts of UV issues that we don't remotely have the tools to understand. So I'm always going to be talking about what has happened when it is mostly evaporated but not fully evaporated.
Do you think that those issues would interfere with having... I mean, I would have said that if they fully evaporated, then the in principle and in practice are the same. And it's hard to reconstruct it.
I think there's still a difference, but there's not an exponential difference. You can look at the limit of what happens when it completely evaporates, and there's an obvious answer. Yeah, it will be as hard as it is to reverse time, basically. Yeah. Right? If you can reverse time, you can get the information. That's pretty hard.
But not,
it's not this hard. This is, it's polynomially hard in the entropy of the black hole rather than exponentially hard in the entropy of the black hole. Okay. So yeah, I want to sort of justify a bit why this sort of second half is going to be much more speculative, much less precise than the first half. It's not that sort of I got a lot worse at physics over the last 6 months of 2019. It's that there's a very important difference between complexity theory and information theory. And it's true even at the classical level. Classical information theory started, of course, with Claude Shannon, and classical information theorists would disagree with me on this, but to a large degree it ended with Claude Shannon, because Claude Shannon proved all the main things you would want to prove about classical information theory. And obviously he was an incredibly brilliant person, but even Claude Shannon, if he turned his mind to it, probably wouldn't have been able to prove whether P is equal to NP. It is just a fundamental fact that complexity theory is a lot harder to prove anything about than information theory. So yeah, that's our sort of partial justification for the fact that we just have some conjectures and some stories and so on. But let's start with the story about how, in principle, you can see information escapes. And as I say, I'm not going to give the full story here. I'm going to give enough of an intuition to understand the second part of the talk. Okay, so let's start by talking about this idea that in some way ADS-CFT is like a tensor network. What does that mean? Well, the idea is that you have a boundary state in a CFT, and in some sense, the sort of bulk description of that state is analogous to a tensor network that prepares a state. So here we have a nice tensor network, a load of tensors with legs joined up, and on the boundary it produces some output state, and the idea is that's the CFT. So it's a fact about tensor networks that if you have a tensor network preparing a bipartite state, say this half of the CFT state and this slightly more than half, then there is an upper bound on the entropy that is just given by the size of the minimal cut through the tensor network. Actually, there's an upper bound that's the size of any cut, but the minimal one is the best upper bound. And for a sufficiently random tensor network, it is a fact that this upper bound is very close to being saturated. So generally, entropies are just given by the minimal cut through a network. So in this sort of analogy with ADS-CFT, then the number of tensor network legs that you're cutting is sort of the analogous to the area of a surface that's cutting through the bulk. And so in ADS-CFT, we have this thing called the Ryutake-Yanagi formula, which says that the sort of entanglement entropy between two parts of the boundary is given by the area of the minimal surface that cuts through the bulk. Of course, in ADS-CFT, you don't just have pure gravity, you don't just have pure geometry, you also have bulk fields sitting in the bulk. And to sort of add these into a tensor network model, what you do is you add dangling bulk legs, so that the tensor network becomes an isometry from some set state of fields in the bulk out to a state of fields on the boundary. And if you do this, then you can now have states where you have entanglement of the bulk fields. They're entangled across the Ryutake-Yanagi surface. I've shown that heuristically here. And these sort of contribute an extra amount of entanglement, contribute an extra legs that need to be cut when we separate into two pieces. And so they add to the entanglement entropy on the boundary. It means that the A over 4 G Newton should really become A over 4 G Newton plus the bulk entanglement entropy across the cut. And this also means that the sort of minimal cut is not necessarily the one that cuts the fewest legs through the tensor network. It's the cut that has the smallest generalized entropy. It's the cut that has the smallest total cut of both bulk legs and sort of tensor network legs.
Can you explain what it means that it makes the network isometry from the bulk state to the boundary state?
Yes, so we can think of this tensor network, these red dots, you can think of as legs coming out of the page, dangling legs coming out of the page. So that could be thought of as one giant state on the red legs and the white legs, but the way we actually interpret it is we think of the red legs as inputs and the white legs as outputs. And so you input some state in the red legs. That's like inputting a particular state of the bulk field. Okay? And then the output of the tensor network is a state on all these white legs at the boundary, and that's your CFT state. So it's a map from bulk to boundary. And yeah, for some class of semi-classical states with certain geometry. So a natural question to ask is, let's say rather than knowing the entire boundary CFT state, we only know the CFT state on part of the boundary. We want to know how much of the bulk does that tell us about? Well, there's a very simple answer in tensor networks, and it also goes through in gravity. The answer is that it's everything between that part of the boundary and this minimal cut, this RT surface. And this is called the entanglement wedge. Why is that? Well, you can just look at this part of the network, and you can think of it as a map from these legs sitting on the RT surface, plus these red bulk legs, to all this stuff on the boundary here. And for the right sort of tensor network, and in gravity, that map will itself be an isometry. Yep?
Here you're specifically talking about the situation where the bulk metric is fixed, and you're talking about perturbative.
Yeah, I'm considering the class of states that have some background geometry and then perturbative bulk excitations about that geometry. Yeah. So yeah, then we have a map from red legs plus the ones we cut here to all the white legs, and that map is also an isometry. So what I can do is, if I have a bulk operator sitting here, I can sandwich that with an isometry on either side and turn it into a white boundary operator just acting on this stuff. So this is the sort of tensor network picture of why entanglement wedge reconstruction works. It's just because we have an isometry that takes us from the unknown degrees of freedom on here, plus all the extra bulk excitations to the boundary. Okay, so I'm now going to sort of slightly switch tack, though we'll see it's sort of the same thing. I'm going to talk about a very simple toy model of how evaporating black holes work. This toy model goes back, I guess, originally to Don Page, and then to Hayden and Preskel, a couple of very famous papers. How does the toy model work? Well, it says black holes are things with a very, very large entropy, okay? But finite, very large but finite. So we're just going to model them with a very large number of qubits. Black holes, for various reasons, we also know have sort of very chaotic dynamics, okay? How do you model chaotic dynamics? Well, the sort of first order simplest thing to do is just consider Haar random states. So this we just take as an input a Haar random state, look at it on a load of qubits, and then we want to model Hawking radiation. We just model that as taking one of these large number of qubits, taking it outside the black hole and calling that the Hawking radiation. Then we take another one and another one and so on. Okay, so it's a very simple, very stupid model of black hole. In that model, so let's say we've had a load of qubits evaporate into Hawking radiation, we're calling that R, and there's a load left in the black hole. We can now ask what's the entanglement entropy between the two, right? This is the thing that Hawking said would just go up forever. Initially, for a Haar random state, if this is some small system, then the state will look maximally mixed on R. Okay, and so the entanglement entropy will be the number of qubits of Hawking radiation. This is sort of Hawking's answer, semi-classical. But when more than half is evaporated, then it's now going to look maximally mixed on all the remaining B qubits, and it's no longer going to look maximally mixed on the R qubits, just because there aren't enough B qubits to purify. So we can think of this as a phase transition in the RT surface of a very simple random tensor network. Right? This Haar random state is just one single random tensor with a load of legs coming out of it. We have to have a cut between B and R. We can either cut on this side of the tensor, or we can cut on that side of the tensor. And the entanglement entropy is given by the one that cuts through fewer qubits. It will turn out that this is exactly the same thing that happens in gravity. The sort of legs on this side will be bulk entanglement between the interior and exterior of the black hole. And the legs on this side will be the horizon of the black hole. I'll explain more how that actually works. Let's talk about one more thing in this very simple model. That's the so-called Hayden-Preskel decoding criterion. Let's say we've thrown some diary into the black hole. We can model that by having sort of a little qubit here, and then a sort of very large isometry into the black hole state. So we're now considering sort of two different black hole states, depending on whether the diary was spin up or spin down. What we see is that in this very simple tensor network picture, what's going on, that diary sits between the cut here and R.
Can you say again what the diary is in this picture?
The diary is this sort of small qubit. This is just this psi is the state of the diary. It's like a single qubit. So we now have a qubit's worth of black hole states we have to consider. We're assuming.
Psi was the state of the black hole in the previous picture, right?
Oh yeah, that's some poor use of notation. This psi is now, yeah, this state, the output here is the whole black hole state. Psi here is just a,
So to make the pictures agree, I would have to draw another state on the left, which represents the black hole before I throw in the diary.
yeah, and then you add in a diary and then you mix them together. Yeah, but I've just sort of absorbed that into this isometry V, just to make the tensor network as simple as possible. So it turns out it's a fact about quantum error correction that as long as the black hole is more than half evaporated, then there is an isometry, an approximate isometry from psi to R. From this reduced state on R, we can recover the state of the diary, psi. So that's just a statement about quantum error correction. But really, it's just a very simple version of entanglement wedge reconstruction. If we're trying to reconstruct from this system R, and this state psi is between R and the RT surface over here. So it's exactly the same story we had in the sort of happy code picture of a big ADS space earlier on. And one aside that I won't really talk about much in this talk is that it's important here that the diary is small. If your diary was like had the entropy of the black hole, then you sort of obviously can't do this because you don't have enough qubits to encode that entire diary. So what about if we, rather than dropping the diary in early in the evaporation, we drop it in late on, after the page time? Well, there's also an answer for how long you have to wait in that case, according to Hayden and Preskill. It's the so-called scrambling time. And the reason for that has to do with the details of how the black hole evaporates, the fact that it's so-called fast scrambling. In particular, you can't see it from this little picture here that I've drawn. You can't see how long. As Raphael said, in that case, you have to remember there's a black hole originally here that's already an input, and it's just about how long it takes for everything to get mixed up. But amazingly, in gravity, sort of RT surfaces in gravity are a bit more sophisticated. You have space-time rather than just a tensor network, and it turns out in gravity, the RT surface even knows that part. So that's the sort of magical part of the story. So let's see what actually happens in gravity. Let's talk about black holes in anti-de Sitter space. Okay? So let's say you make a black hole by collapse in anti-de Sitter space. What happens? Well, we'll start to Hawking radiate. You have modes outside the horizon entangle with modes inside the horizon. These modes will escape the black hole, go off to the boundary. But then it's terribly boring. What happens is they hit the boundary and they bounce back in. So the black hole does not evaporate. So we have to do something slightly different to make the black hole evaporate. And that's we have to replace the reflecting boundary conditions that we normally have in ADS-CFT with boundary conditions where this Hawking radiation gets absorbed. I'm just going to absorb it into a sort of second bulk. Okay? So the second bulk would have a boundary. That boundary is just a second holographic CFT. These holographic CFTs, two holographic CFTs from a boundary point of view, will become entangled over time as the black hole evaporates. And we expect, if we believe in unitarity, that that entanglement should follow the page curve. Okay, so let's see how that happens. Well, I claimed that a tensor network was analogous to sort of a slice through the bulk. So here's an example of a slice through the bulk. I've drawn it in blue. That's a Cauchy slice through the two copies of the bulk, two different bulks that are entangled. And you might be saying, hang on, can we really think that any arbitrary slice through the bulk is a tensor network? You can't. But for the moment, I'm just going to pick a particular slice, which is going to be sort of a traditional nice slice that Hawking would think about, that sort of sticks near the horizon. And I'm just going to claim that that's going to be analogous to a tensor network. And I'll be a bit more precise about what slices actually are analogous later on. So what does one of these nice slices look like? What does it have? Here is a very, very schematic Lenny Susskind style drawing of that nice slice. We have the boundary of the black hole over here, right? Then we have a horizon here, and then this is the interior of the black hole. And you'll notice that I've drawn the sort of thing narrowest at the horizon, right? It's because the black hole has been evaporating. As we go behind the horizon, if we stay on a nice slice, if we don't go near the singularity, then we're effectively going backwards in time. So we go backwards in time, the black hole gets bigger, because as we go forwards in time, the black hole gets smaller.
So just to be clear, this space, so this is one time slice?
This is one time slice.
The universe is everything to the right of the black line?
So the boundary of the sort of holographic, the exterior is everything to the right of this sort of narrowest point. The interior is everything to the left here. And then these blue lines schematically represent that you have these interior modes sitting here that are entangled with stuff here, which is the second bulk.
But as far as the first bulk is concerned, everything to the left of the black line doesn't exist.
Yes,
The entire
yes.
first bulk is the right of the black line.
The first bulk is sort of filled in like here and then going out over here.
Okay.
Yeah. Is that clear to people? These are very schematic drawings, and some people seem very confused by them. I think I spent too much time with Lenny. These make perfect sense to me. Imagine this is all shaded in. This is this is a wormhole, right? I've drawn it as sort of a cylinder, and then it gets wide at the end. This is where it gets out to the boundary, right? So then, you can think of this as a shaded area. This is the sort of where this slice hits the horizon of the black hole. So you go further and further left, we're sort of getting into the interior of the black hole, and it's getting gradually bigger as you go back in time.
You mind going back to the previous slide?
So this is the slice we're drawing. So there's this bit over here that's in the second bulk, okay? And so that was the circle I drew at the top.
The cloud.
The cloud, yep. And then that cloud, this stuff, these Hawking modes and that cloud were entangled with these modes in the interior of the black hole, right? That's these blue lines entangled between the cloud and this blob is the interior. And then as we go along this blob to the right, we're getting closer to the boundary of that CFT. This point is the horizon, and then the area starts getting bigger as you get outside the horizon.
Maybe drawing the bottom half may have confused.
Sorry?
Maybe drawing the bottom half may have confused people.
Yeah, I think so.
The article
Yeah.
here, just, anyway.
Yeah. This is how Lenny draws black holes in his quantum information and quantum gravity classes. If you haven't taken one of them, then you haven't lived. So, you shouldn't be in this room. Okay. He doesn't draw the blue lines. Those are purely me. So you're allowed to be confused about them. So if we think of this as analogous to a tensor network, there's sort of two possible minimal cuts through it, right? There's one part where it gets quite small, which is up here. There's sort of a constriction near the horizon here, where the area gets smallest. And there's another one, which is just to cut through all this bulk entanglement and not have to cut through any area at all, right? We're trying to have a cut between this cloud and the right boundary over here. Before the page time, when we haven't been evaporating very long, then the smallest cut is this red line, right? Because we don't have very much bulk entanglement. It hasn't been evaporating very long. There's this huge area term if you want to try and cut through the horizon. So the smallest cut is to just cut through here. What answer does that give to the entanglement entropy? It just gives what we're cutting is purely bulk entanglement. We're not cutting any area. And so it just gives the answer that's the Hawking answer. It's the semi-classical entanglement between the interior and the Hawking radiation. What about if there's some diary sitting in the interior of this black hole that we threw it? Well, it lies between this cut and the sort of boundary of the original CFT. So in analogous tensor networks, we can sort of push it through the tensor network out to this boundary. It's in the entanglement wedge of the original CFT, i.e. it's encoded in it. It means no information has escaped from the black hole. It's still in the entanglement wedge of the original black hole. It's not come out into this second holographic CFT. What about after the page time? Now the sort of smallest cut is going to be the one that just cuts through the horizon area, right? By definition, after the page time, the Bekenstein-Hawking entropy of the horizon is smaller than cutting through all this huge amount of bulk entanglement. The black hole's been evaporating for a very long time. So that means now, this diary, we can push through our sort of tensor network analog and push it out to this second holographic CFT, secretly encoded in the Hawking radiation once we've waited for longer than the page time. Okay, so I apologize for not having been able to give that story properly, but I do want to get on to the main thing I'm sort of wanting to talk about in this talk. So I'm just going to say some brief further comments. I just sort of chose an arbitrary slice through the bulk here. And as I said, the analogy to tensor networks is only really valid for certain slices. In fact, the slices that it's valid for are the slices that make this sort of min cut as large as possible, where you maximize this minimal generalized entropy cut. And this is something called, the cut is then something called the minimal quantum extremal surface. When you do this all properly, when you choose the right slice in this way, what you find is that you get things like exactly the right scrambling time delay for information to escape the black hole and so on. I also want to emphasize that even though I have not done so in this talk, everything I have said up until now follows purely from gravitational path integrals. What you have to do is you have to do the replica trick, and then you find that there are topologies that include space-time wormholes and that give you exactly these answers. Okay, the analogy with tensor networks is just an analogy that all goes through beautifully, but you wouldn't need to know anything about tensor networks to get these answers. I have said a lot about tensor networks and nothing at all about replica tricks, because for the rest of this talk, we're going to be going beyond what you can actually calculate with gravity. Yeah, Nick?
So I just wanted to understand the first point that you were making here.
Yep.
From the perspective of like pushing the diary in the way that you're talking about, which I assume from the tensor network perspective looks like isometric pushing, like the greedy algorithm.
Yeah, exactly.
Should I think of this as a necessary condition, a sufficient condition, or a necessary and sufficient condition for the isometric pushing for it to be successful?
So the region in gravity that you can push it for is the entanglement wedge. Any point in the entanglement wedge is contained in a Cauchy slice that also contains the quantum extremal surface. And so, but it's not necessarily one that has a maximal min card.
So this is like a sufficient condition, but not necessary.
You can think of it as necessary though, because you can choose a Cauchy slice that has that, and then the operator you want will be encoded in that Cauchy slice in the right region. So I would say it can be thought of as necessary as well. Okay. So for the rest of this talk, I'm really just going to be relying on this analogy with tensor networks. Possibly I'm taking it further than it's actually justified in going, but it's going to give some nice results that are consistent with everything else we know. So we'll see what happens. Okay, so let's move on to the sort of actual main part of my talk, which is why is it the case that it's so difficult to actually decode any information from the Hawking radiation, even though it's in principle possible. So this is, of course, a famous claim by Harlow and Hayden, the original people who really made this claim, which is that if you have black hole and Hawking radiation, you let it evaporate for till it's more than half evaporated. So in principle, the information you want is encoded in the Hawking radiation. It's still exponentially hard in the Bekenstein-Hawking entropy of the black hole to actually pull that information out, to say convert that complicated state of black hole plus Hawking radiation into a simple state. Say convert it into a thermofield double, and then everything's in a very simple state, and you can just pull the information out almost trivially. Okay?
By hard here, you mean the number of simple gates you would...
Yes, so what I mean by this is if you have a quantum computer and you want to apply simple unitary gates that maybe act on a few qubits of Hawking radiation at a time, then the number of those gates that you need to apply is e to the order Bekenstein-Hawking entropy of the black hole. So there's also a claim that was made slightly later, but has been made in many papers since by Susskind and collaborators, that the complexity of states, say black hole plus Hawking radiation, in quantum gravity is dual from a bulk perspective to the volume of, say, a maximal volume slice through the bulk, or the action of a Willard-Witt patch. There's several proposals, but they all basically say it should be dual to something like volume. For an evaporating black hole, or actually for any black hole, then volume grows linearly with the time you let it evaporate for. So this will give an answer that this complexity of the state of an evaporating black hole after the page time is order the black hole entropy. Right? That's how long we have to leave it evaporating for until it's more than half evaporated. So this seems like a bit of a contradiction. So how do we resolve this contradiction? Well, I guess one possibility is to say, look, Lenny's quite old these days. Complexity equals action. Do we really believe any of that? But we really, I don't know, we may not believe it in full generality, but at least in this case, it's certainly the case that you can make the state of the evaporated black hole in an order entropy time, or you can unmake it in the same time. In fact, all you do is you make it the same way that gravity does, You form a black hole by collapse and you let it evaporate. That takes order entropy time. You can discretize that process into a load of gates, and the number of gates it will take will be order the entropy. And as everything's unitary, I could also do that backwards. I could take my final state and go back to my simple initial state that the black hole formed from.
To me, the statement with first is like you can take arbitrary superposition, right? That's why it's exponentiated. No basic.
I'll get to, yeah. I think it's not quite that edgy. So it seems like Lenny's not wrong, at least in this context. So what about Harlow and Hayden? Maybe they just screwed up. They obviously knew this fact too, that you can make this black hole in short time. The reason they said it was exponentially hard is that they were talking about something slightly different to what Lenny's talking about. They were talking about different rules for what you can and can't do. And that's that they were talking about what we call the restricted complexity, whereas the thing that's supposedly meant to be dual to volume or action is the unrestricted complexity. So what are the rules for what the restricted complexity is? It means the following. Let's say you start with some simple entangled bipartite state, say like a thermofield double state, or like a product of a load of Bell pairs. Okay? The restricted complexity of getting from that state to some other state you want to produce is the number of sort of simple gates you need to apply to each of the two sides in order to get the state you want. But they have to be states that either act on one side or the other side. You're not allowed any gates that couple the two sides together. So for example, we've drawn a sort of network here. Each of these sort of links is like coupling two qubits together and interacting them. And we do a load on this side, and then we do a load on this side, and that makes some state. Of course, if you started with a maximally entangled state, then it's a fact that you can sort of always move all the ones on this side over to this side, right? You can just push them through the product of Bell pairs that you started with. So this tells you how, So say you started with a thermofield double state, or you start with your evaporated black hole, and you want to turn it into a thermofield double state, but you're only allowed to act on the Hawking radiation. This left-hand side, this restricted complexity, is how hard it is to do that. Okay? Lenny is talking about something different when he talks about complexity equals action. He's saying you're allowed arbitrary gates that are allowed to couple the two sides together. So these red things you can think of as gates that couple something on the left to something on the right. Yep?
To be completely clear, like a specific thing that you could do then is to just send to time reverse, which means you send
exactly.
back into the black hole, and that's the interaction you're talking about.
Yeah, exactly. So in particular, as Raphael says, the easiest way to get back to a simple state from this complicated state is just to do time reversal. And when you do time reversal, you're taking that Hawking radiation, you throw it back into the black hole, and then the dynamics of the black hole are presumably coupling it with all the other stuff in some complicated way. And so it's this sort of, the ordinary time evolution is like this thing, and it's not like this thing. So the conjecture of Harlow-Hayden plus Susskind and co. is that even though this is easy, this is really, really hard to get from your mostly evaporated black hole into a thermofield double state. Yep?
How does locality play into this unrestricted complexity picture?
Yeah, how it plays in is that you're only allowed, the individual gates are only allowed to interact, say, 2 or 3 or 4 qubits at a time, but they're allowed to interact an arbitrary choice of 2 or 3 or 4 qubits, right? So the first gate could couple qubit 1 to qubit 7, and then the next qubit 7 to qubit 4, and there's no restriction in terms of which side the qubit.
So it's k-local, but not like spatially.
Yeah, exactly. That's the normal version. Yeah. K-local, no spatial locality at all. Yeah. So this is
Not just like if you allow some arbitrary superposition not in a preferred basis, or you allow arbitrary superposition of radiation of black hole. For the gate for operation, the number of gate is exponentially smaller. It's not it's something not like that.
Sorry, the number of gates is order the entropy if you're allowed to couple arbitrary things together, right? Because you can just undo the time evolution. Yeah.
Because you allow this arbitrary superposition in arbitrary pairs.
Yeah.
and not in preferred basis or something like just radiation and just.
Yeah, exactly. Yeah.
Then the number of bits is exponentially smaller.
Yes, yes. So yeah, if you're only allowed to act on Hawking radiation, you have to spend an exponentially long time doing it. If you're allowed to act on both at once, it only takes a linear time.
Yeah, yes, I want to make sure what
Yep.
I said was not.
Yep. Okay. So the question we wanted to answer in this project, the big question we were trying to see, is how can you tell from gravity when you have this huge gap between the sort of restricted complexity, how hard it is to decode just from the Hawking radiation versus how hard it is to decode by acting on both at once. Let's take an example where this isn't true, just to have a point of comparison. Say you just take the thermofield double state and you just evolve one side for sort of order the entropy of the black hole time. Right? We now have a state whose unrestricted complexity is order the entropy of the black hole, it's equal to the volume, but so is the restricted complexity, because to make it we only acted on one side. We didn't couple the two sides together or anything like that. Okay? And seemingly this looks kind of similar, right? They both involve a wormhole that's order the entropy in length, both this and an evaporating black hole. But the restricted complexities are exponentially different.
I didn't understand what you're doing. Are you evolving the thermofield double state on one time?
Yep.
On one side only?
Yeah, just on one side only for order the entropy in time.
But then it's trivial, is it true that, I mean, since
Yes.
you're all only on, okay.
Yes, exactly. My point is that it's trivially true that they're equal in that case, but what we wanted to know was how you can see the difference, right? In both cases, you have a wormhole that's order the entropy in length. So it's not like a wormhole that's order entropy in length automatically has this incredibly large restricted complexity. We wanted to know if there's some geometric property that the evaporating black hole has that the thermofield double state, evolved thermofield double state does not, that creates this gap. Okay? Yeah.
Just a quick question also for normalization. If I had evolved the thermofield double state on both sides, it would be
It's same.
from a maximum state? Or?
No, if you evolved on both sides, then I can convert that into just evolving on one side.
Even
Yeah.
though it's not maximum?
And
You just need full rank, I think. You don't need-
Yeah,
it doesn't
exactly.
need full rank.
Yeah.
Good, good.
Yeah.
Thank you.
it's really, yeah.
Yeah.
Yeah. Okay. And yeah, our answer to this question is going to be that evaporating black holes contain what we call a Python's lunch, whereas a time-evolved thermofield double does not. And it's that Python's lunch that makes it really, really hard to get the information out. Okay, so what on earth do I mean by a Python's lunch? Well, in a tensor network, I mean something like this. As you see, we have end of a Python, and we have a big bulge in the middle. That's the Python's lunch. So what specifically is going on here? We have a tensor network where the tensors, so we have sort of unitary tensors interacting things up here, right? We have some unitary circuit being applied, but then at a certain point, the number of qubits gets bigger, right? So we have tensors that go one leg as an input and then two legs as an output. So these tensors I'm going to assume are isometries, which alternatively can think of as a unitary where we input some extra qubits in a fixed, say, 0 state. Right? So we start with a small number of qubits here, number of qubits gets bigger, and then the opposite happens. Number of qubits gets smaller. We're applying like the adjoint of isometries here to get this number smaller. If the left-hand side of the network has fewer qubits than the right-hand side, it is a general fact about tensor networks that the whole network will, up to a tiny error, generically be an isometry from left to right. Right? Just general fact about maps from smaller number of qubits to bigger number of qubits, unless you do something very weird, they end up being an isometry. However, if we look at the individual steps in the tensor network, they're not all unitary. Why? Because we have this bit where it gets smaller, and the map from, say, a line here to a line here is very, very not an isometry. It's going from a larger number of qubits to a smaller number of qubits. It literally can't be an isometry. It's actually an isometry in the opposite direction. Okay? So that means even though this tensor network might be pretty small, might be a simple tensor network, just randomly might be order the black hole entropy in size, its length from one end to the other, the size of the sort of unitary circuit you need to construct it as a unitary can still be a lot larger. Is that clear? So the tensor network is unitary, but it cheats and has individual steps that are non-unitary. It's just the end product they cancel out. And what we want to know is how hard it is to construct a sort of circuit where all the individual steps are unitary. Whoop. So let's see this more explicitly. So looking at this tensor network as a map from left to right, we have some input state that I'm going to call I. Okay? That has some unitaries applied to it. It then has some extra qubits added in a fixed 0 state. Right? We add in a load of extra qubits, get a state up here, have a bit more unitary stuff applied, and then we have the adjoint of adding in qubits. And the adjoint of adding in qubits is post-selecting onto the qubits being in a certain state. So we post-select on them, we apply a bit more of a unitary, and we end up with some output state psi. Okay, so I'm going to take all the unitary stuff, and I'm going to call that U subscript Tn. Yep?
So ML is the difference in height between left
Yes.
and the top, and MR is the other difference?
Yes, exactly. Yep. ML is the increase in size here, MR is the decrease in size there. And I've said that the right is bigger than the left, so we want ML bigger than MR. Okay? So yeah, this UTN is just the simple sort of unitary, relatively simple unitary evolution that the tensor network is doing. What we want to know, what we want to know is how complicated a unitary do you need in order to do this without having this post-selection here, right? I said that the whole map from left to right was a unitary, so there must exist some unitary that I call UPL, UPython's lunch, that does the whole thing for you without having to cheat and use post-selection. Okay? But that unitary is not necessarily simple, even though this one is. And our task is going to be to work out how complicated it is. Okay. So how hard is it to bypass this sort of post-selection that the tensor network used and just do the whole thing via a unitary circuit? Well, there's one sort of obvious approach, which is the most naive thing that you could try. Let's say you were allowed to make the input state lots of times. And if you fail to make the output state, you could just give up and try again. Right? Well, then what you could do is you could just apply this simple unitary, UTN, and then you could measure all the qubits you want to post-select on. And if you got 0 for all of them, then you go, yay, I'm done. And if you don't, you just try again. Well, that's an approach. It would eventually work. But how many times would you have to do it? Well, it's order 2 to the MR. Right? We have MR qubits. You have to get all of them be 0 when you do these measurements. Roughly a 50-50 chance on each of them. So it's incredibly small probability. You have to wait this incredibly large exponential time. Also, you're not really doing a unitary here. You're doing repeated attempts at a unitary plus measurements, so it's cheating anyway. But I say it because it gives intuition for what the right answer is. And that's because this is doing a sort of very naive search. It's doing a very naive search for the right outcome just by doing measurements and repeating until you get the right one. And we know in quantum mechanics there's a better way to do a search, which is unitary, which is called Grover search. So this is the sort of better approach to doing this. I'm not going to go into the details of Grover search for people who don't know it, but it's this, it's one of the 2 quantum information algorithms that actually exist and are potentially useful for things. And it basically works as follows. You start with your input state, right? Your input state plus your ancilla qubits. Then you apply this simple unitary UTN. Then what you do is you apply a phase. You apply a phase of -1 if and only if all MR of the qubits you want to post-select on are all in the correct 0 state. Any orthogonal state, you don't apply that phase of -1. So this just changes the state very, very slightly. There was an exponentially small amplitude of being in that state, and there's just this tiny exponentially small change in the state. Then you apply U-tensor network dagger, and you go back to the initial state. Well, not quite the initial state, because there's now an exponentially small error. And now you apply a phase if all ML of the initial ancilla qubits are in the 0 state. I.e., if the state hadn't changed, this wouldn't do anything. This would just apply a phase of -1, right? But because there's now this slight error you've induced, it won't quite apply a phase of -1, because the slight correction to the state will behave differently. And then you just repeat this process. You have to actually repeat this process 2 to the MR over 2 times. It's not 2 to the MR, it's 2 to the MR over 2. This is the famous Grover quadratic speedup. And each time you just have a tiny exponentially small correction in the state. But what it ends up doing is it very, very slowly rotates the state round from the state you started with to the state we actually want to end up with, the post-selected state. And eventually, you actually do get that exact post-selected state up to this incredibly high accuracy. So this is still exponentially hard. So this is consistent with the idea that there's no way to do this UPL, to do this unitary circuit, to pull out the information black hole as it will end up being without taking an exponentially long time to do it. Yep?
So should I also here think about the fact that the query complexity logron for Grover search is tight?
Yeah, I refer you to my next slide. So we just did this one particular way. You might very well ask, okay, sure, you took an exponentially long time to do it, but you might just be stupid. Could there be a more efficient way to do it? And the answer to that is maybe. The answer to that is nobody knows anything in complexity theory. One of the few things that is known, as Ning said, is that if you're just searching for something, if you have a black box and you don't know anything about what you're searching for, but you know you're searching for something, then Grover search is provably the best way you can do it. So in this case, we are searching for something, right? We're searching for the things we want to post-select onto. But we sort of know some stuff about what's going on. It's not like a pure black box setting, so it's not impossible there's a more efficient approach. One thing you can say is that there's very strong reasons you can't generally do post-selection in polynomial time. And the reason for that is that that would imply that BQP equals post-BQP, which is equal to PP. So that may not mean anything at all to many of you. Honestly, doesn't mean a lot to me. But if you suggest that this is true to Scott Aronson, he will laugh at you. So I think that means we should all believe that it is not true. So what does it actually mean? PP is a classical complexity class that is incredibly, incredibly powerful. It's basically, yeah, it's much more powerful than something like NP. It's this huge class. BQP is stuff that quantum computers can do. Okay? Stuff that quantum computers can do in a polynomial time, to be more precise. Post-BQP is stuff that you can do with a quantum computer if you're allowed to do post-selection. Okay? So if you could simulate post-selection in a polynomial time, then BQP and post-BQP would be the same thing. And we know it is known, proved in fact by Scott Aronson, that post-BQP is equal to PP. It would mean that quantum computers can solve anything under the sun. They would be able to solve traveling salesmen. They'd be able to solve incredibly, incredibly powerful things.
Why doesn't your third bullet point make this implication not fully tight? Because that would be true, I think, if you could fix any post-selection with a quantum computer. But here you're still.
Yeah, I agree. Yeah, again, it's possible that in the particular case, then there is a faster way to do it. Yeah, but I think this is sufficient to show if you have a generic arbitrary tensor network with an arbitrary post-selection, then you generically can't do it in polynomial time. The things that show up in gravity, who knows? But we generally like to say gravity is generic, doesn't have fast speedups, blah, blah, blah.
Can I go back to the picture? Because I want one more.
Yep.
The scenario. This diagram of lunch.
Yep.
Yeah.
There.
can I just view from physics that you may want to avoid Biot-Planckian physics, but forget about that.
Yep.
The left is something like the initial state of the collapsing matter, and interior is the whole, and then the final.
I will get to that in a slide or two. We'll see how this shows up in, Okay. But first, so if this is the optimal way to do it, if there's nothing faster than Grover search, then we get this conjecture for the complexity of the state produced, restricted complexity of the state produced by a Python's lunch. Okay? So it's just proportional to how complicated your tensor network was in the first place, times 2 to the number of qubits you needed to post-select on, divided by 2. Okay? Okay, so this will hopefully answer your question. Well, actually the next slide will. So what does this have to do with gravity? Well, again, by the analogy between tensor networks and a slice of the bulk in ADS-CFT, we would say that sort of a normal wormhole, say the time evolved thermal field double state, sort of starts largest at the left, at say the left boundary, and then as you get near the center, it gets smaller and smaller and smaller, and then it starts getting bigger again. Okay? The conjecture would be that a wormhole that looks like that has a small restricted complexity. Restricted complexity that's roughly equal to its unrestricted complexity. You could have another sort of wormhole. You have a wormhole that gets really small, and then it has a big bulge in the middle, and then it gets smaller again, and then it goes out to a boundary on the right-hand side. This is what I would call a Python's lunch wormhole. It's analogous to that tensor network that got small and big and small again. The conjecture would be that Python's lunch wormhole has an exponentially large restricted complexity. Okay, let's go back to our slice through an evaporating black hole. We have our Hawking radiation out here. Then we have this sort of candidate minimal cut that cuts through all the bulk entanglement of the Hawking radiation. And we have another candidate minimal cut that's the sort of constriction at the horizon. And in between the two, any way of sort of slicing from one to the other will get bigger. We'll have a bulge in the middle. So this evaporating black hole, unlike the time-evolved thermofield double state, contains a Python's lunch.
I'm so sorry. This picture looks like the previous one?
This is the same picture as the previous one. I'm just talking about it in the context of Python's lunch. It's exactly the same picture as the previous. So
where's the bulge?
Yeah. So let's say we're sort of thinking of slices going through from this end to this end out here. I'll start at this end, right? Starts getting smaller, starts getting smaller, starts getting smaller. Has a smallest point here. Now it starts getting bigger again. And in fact, at this point, you're not just cutting through this stuff. You'd also have to cut through a bit of bulk entanglement. So it's even bigger than you think. And then even bigger, gets bigger and bigger and bigger. And then eventually you reach the end, and all the area disappears, and you're just left with the bulk entanglement. So at that point, it's got smaller again. I'll show on the next slide more explicitly how it bulges and then gets smaller. Yeah?
Also, Geoff, a bit of a naive question. So the amount that you need to post-select is the thing that actually goes to the exponential, right?
Yes. Yes.
Exponential complexity.
Yes.
So what would be the analog of that MR? Would that be the difference between how big the bulges are? Or?
It's the difference between the size of the bulge and the size of the larger constriction at the end, okay. Right? That's the amount you post-select. You start at the smaller constriction, you add stuff in to get the maximum size, and then you post-select to get to the larger minimum. Difference between the two is, yeah, I'll get to that. I'll get to that. This is hopefully answering your question. So, yeah. So the size of the lunch, how big it gets in the bulge, depends on how you sort of slice from one end to the other, right? Let's draw a slice, and then I can explain. So one way of sort of slicing through from the sort of, the end with the Hawking radiation to the end of the horizon is you start at just cutting through the bulk entanglement, right? At that point, it's like relatively small. Then you start at the very end of the wormhole. You have a load of extra area that you've now added in. It's got a lot bigger. Okay, the cut is now cutting through all the bulk entanglement, and it's cutting through a load of area. And now you gradually move that slice along. So now this area gets a bit smaller, and you're cutting through less bulk entanglement. So it's now getting smaller again. And it keeps getting smaller and getting smaller and smaller. And eventually it ends up just cutting through this very end here. Right? And at that point, it's even smaller probably than when it started, because now we're not cutting through any bulk entanglement. We're just cutting through the horizon area. Okay? So that's one way of slicing through. And in this case, the sort of maximum size is this thing here, right, where we're cutting through all the bulk entanglement and we're cutting through all the initial horizon area of the black hole. Okay? But there's a lot of different ways you could slice through it. The sort of most efficient way to do the Graver search will be to have as little post-selection as possible. You have as little post-selection as possible by making the size of the bulge as small as possible. Right? So you want to slice from one minimum to the other in a way that makes the bulge as small as possible. So in this case, the maximum size was all the bulk entanglement plus the initial horizon area. There's an alternative option, actually. And that's, rather than starting at this end, you start with a double cut at this end. So you have cut through all the bulk entanglement, and then you cut through twice through the sort of final horizon area of the black hole. And then you move one of those cuts backwards along the wormhole. As you move it backwards along, the area increases, but the bulk entanglement decreases. The second effect is actually larger than the first. And so again, the sort of largest size of the bulge is here, where you've just created this double cut up the end of the final horizon area. So in this case, the sort of maximum size of the bulge is, again, all the bulk entanglement, but now it's twice the final horizon area of the black hole. So if the black hole is more than half evaporated, this approach is going to be better than the previous approach. It's going to be more efficient. It's going to correspond to a sort of more efficient way of doing the protocol. Worth commenting, we often say that the page time is when the horizon area is half the initial horizon area. Page time is actually when the horizon area is a bit bigger than half the initial horizon area. This transition actually happens when the horizon is half the initial horizon. So it's not at the page time. So if we plug in, it turns out these two are the most efficient ways of slicing from one to the other. Yep.
So that means, I mean, this whole thing is only relevant after the page time when you can actually reconstruct.
Well, no, before the page time, it's telling you how hard it is to reconstruct just from the black hole. Or how hard it is to turn the whole state into a thermofield double state. It's still telling you stuff before. Yeah.
So both slicing protocols are relevant in some regime.
Yes. Yes. Both slicing protocols are relevant after the page time as well.
Yeah, and pick
yeah.
after page time.
Okay. So yeah, if we sort of convert our tensor network formula and replace sort of the number of post-selected qubits with differences between generalized entropies, then what we get, yeah, this is the amount of post-selection. We can get this plot for the log of the restricted complexity of pulling anything out of the black hole. What you find is it goes up linearly until the page time, which I have assumed is when the black hole is 40% evaporated. That's like roughly right. Then there's a while. So yeah, initially the complexity grows exponentially because the number of post-selected qubits grows linearly, and it's exponential on that. After the page time, then the larger of the two minimal surfaces is no longer the sort of cut through the bulk entanglement, it's the cut of the horizon. And that actually causes the complexity to roughly saturate. It stays constant for a while. Then you hit this second transition where the sort of more efficient way of going through is not to sweep forwards along the wormhole, it's to sweep backwards along the wormhole. And once that's the case, then the complexity starts decreasing exponentially, goes linearly downhill from the log point of view. Eventually, when the black hole has completely evaporated, then sort of by definition, the restricted complexity has to be equal to the unrestricted complexity, and so it ends up being order the Bekenstein-Hawking entropy. You do get the right answer, you end up with no post-selection, and you get the right thing. Okay, so I know I've taken longer time than I meant to. I'm just going to briefly, to try and emphasize that I'm not going off into crazy land here, I'm just going to go back to this very, very simple toy model of black hole, and we're going to see how exactly the same thing happens in it. Okay? So here's my toy model of a black hole, right? I was calling it a hard random state before, but now I'm going to make it instead, it'll be some simple state, and then we've applied a simple unitary that couples everything together, right? UTN. It's the equivalent of that before. And what we want is to find a U that starts with a maximally entangled product of Bell pairs and outputs the same state as this UTN while acting only on the Hawking radiation. I've got it acting on the black hole here, but never mind. Reverse the labels. How can we do that? Well, the answer is it's very, very simple. We're just going to take this R system here, and we're going to wiggle it around a bit, like so. Make a little snake. So now we have, this is graphical notation. You can do whatever you want. But now this is interpreted a different way. Now this is starting with a simple state here and a product of a load of Bell pairs, right? And then we're applying some complicated system that doesn't act at all on this, and it only acts on all this stuff. So unitary, that's UTN. It's a pretty simple thing to do. But then we have this. This is post-selecting onto a product of a load of Bell pairs. How many Bell pairs? Well, it's A horizon over 4G Newton of them. So it's actually post-selecting onto 2 A horizon over 4G Newton. So yeah, this corresponds to the reverse sweep through the tensor network. This gives the answer of what we want at late times. Okay? And so it's exactly the same thing, exactly the same sort of post-selection you get in a simple time model, as I claimed you got by analogy with tensor networks and gravity. There's another way you could do it. This is, again, taking the same diagram and just flipping things around and reordering stuff in space. Now, it looks like taking a load of Bell pairs up here and Bell pairs down here, applying the dagger of U-tensor network, and then post-selecting onto the simple 0 starting state that we started with here. This is post-selecting onto the initial horizon area number of qubits. So this actually corresponds to the forward sway sweeping the black hole. Okay, so they're both things that show up in simple time models. There is a slight difference between this time model and the real things. You don't get that flat peak in the restricted complexity that I had in gravity. That's just because for this simple time model, the page time is exactly at half the number of qubits, because the sort of number of qubits involved isn't increasing over time. Yeah. Okay.
You could also do that graphically, right?
Yeah, exactly. Yeah, you would have isometries at each stage that you add in an extra ancillar qubit at each time you take out a bit of Hawking radiation, and it would then go through the same way. Okay. So as I said in the first half of the talk, everything I said now was just talking about one arbitrary choice of Cauchy slice, and we really don't want to be doing that. We want to be defining everything that we work with covariantly. So the sort of minimal cut in the tensor network, as I said in the first half of the talk, corresponds to the minimal quantum extremal surface. Okay? And this can also be found by taking the minima surface within a single Cauchy slice and then maximizing that minima over all Cauchy slices. The other sort of end of the lunch, the other constriction, is just another quantum extremal surface, a non-minimal quantum extremal surface. What we want to know is what the covariant definition is of the size of the bulge, like a definition that doesn't just involve an arbitrary way of slicing through an arbitrary Cauchy slice. So for the tensor network, what we had to do is we had to consider all ways of slicing from one way or the other, and then we looked at the maximum cut within that way of slicing through it, and then we minimized that maximum. It was a mini-max surface. So our conjecture, based on that, plus the fact that maximin works the way it does, is that the right covariant definition of the sort of size of the bulge is a maxi-mini-max surface. You start by picking a Cauchy slice. You then pick a way of slicing through that Cauchy slice from one quantum extremal surface to the other quantum extremal surface. You look at the maximum size, maximum generalized entropy within that slicing. Then you minimize that over all ways of slicing. Then you maximize the resulting mini-max thing over all Cauchy slices. So if nothing crazy happens, and there's no reason to think it does, if everything goes through, subject to the usual provisos you need to make about maxi-min, then this will also be a quantum extremal surface. So our conjecture is the sort of covariant notion of a Python's lunch is a set of 3 quantum extremal surfaces, sort of small, big, medium, all in a line. And the big minus medium is telling you about the amount of post-selection. It's telling you about the complexity of pulling anything out of the lunch.
I'm sorry, can you just go back to the previous slide?
Yep.
So you're looking for 3 extremal surfaces.
Yes.
And 2 of them are found using the usual maximum prescription, but starting from different ends. And then this is what you're describing here, the maximum.
There will only be one, there will only be one that's found by maximin. What you can argue is that if there exist at least 2, then there will generically exist a set of 3 that look like sort of small, big, medium. Think of it as like, let's say if I have a function with a minima, right, then I can just have one minima. But if I have a second minima over here, then I will always have a saddle point in between the 2. Yeah.
What I'm asking is, which of these surfaces is being constructed by the maxi-minimax? Is it the one in the middle?
The maxi-minimax is the one in the middle, yes. The maxi-minimax is the one in the middle. Yeah, so for an evaporating black hole in simple time models, we can explicitly find the sort of quantum extremal surfaces that correspond to this maxi-minimax thing. So for the sort of forwards way of sweeping through the slice, then it's a quantum extremal surface that sits inside the collapsing matter that forms the black hole. So it's right down at the end of the wormhole when the black hole originally formed. Its area is A0 over 4g Newton. Its generalized entropy turns out is basically the Beck-Inston-Hawking entropy because all the interior partners of the Hawking radiation are really close to the horizon at this point. The thing that corresponds to the sort of reverse way of sweeping is the union of 2 different spheres, these 2 black dots here in a Penrose diagram. So it's like a double cut, and it sits just inside the sort of actual minimal quantum extremal surface. Again, this can be found. In this case, it's only possible to find it explicitly in J2 gravity plus free fermions, just because entanglement entropys of 2 intervals are hard, but it can be found. So basically out of time, but fortunately this is the final slide. So just some final comments on things you should take away from this talk, hopefully. The first is that non-minimal quantum extremal surfaces deserve some love too. They're not just like failed things that didn't turn out to be minimal and didn't turn out to be relevant. They actually seem to control some important stuff. This comment was originally written at Santa Barbara because there was a lot of talk about how beyond geometry and how we need to start understanding the microstates of black holes beyond semi-classical geometry. I think the semi-classical geometry still has a load of things it can teach us. We shouldn't all move on. So it turns out that even the unrestricted unitary circuit complexity isn't actually dual to volume or action. If volume or action is dual to anything, then it must be dual to more like the size of the tensor network needed to make the state. You need to allow post-selection when you prepare states if you want to have complexity to be dual to volume action. I didn't have time to talk about that. There's also, this is something Arvin has been thinking about and some other people. This suggests that entanglement wedge reconstruction should only be sort of hard when it's behind a non-minimal quantum extremal surface. If it's in front of any non-minimal quantum extremal surface, it shouldn't be hard, even if it's outside the causal wedge. So it suggests we should try and look for sort of ways to do entanglement wedge reconstruction that will work in that case, that are sort of simple or semi-classical in some sense. And you can talk to me about that if you want to, or talk to Arvin. He's maybe working on more. Final sort of side comment. Actually, it turns out Harlow and Hayden overestimated the complexity of decoding the Hawking radiation by a square root factor, basically because they didn't think of this Grover search protocol. For all the things they considered, this Grover search protocol will work, and it's a square root improvement of what they did, but it's still exponential. Thanks.
I have a pretty basic one actually. In the the forward and backward sweeping pictures.
Yep.
Where are you picturing the bulge in those diagrams?
Yes. So let's. So, yeah, the point of the bulge is that there's a pretty small cut here, right? And then when we introduce a sort of double cut here, as we start to sweep from one minima to the other minima, it gets a lot bigger. So the sort of biggest point, the largest cut is here, right? The bulge is like, let's just do a sort of more heuristic bulge. Whoop. Right, if we cut through here, it's pretty small. If we cut through here, it's a lot bigger. Then we cut through here, it's small again. Right, as you want to sweep from one cut to the other, it has to go bigger before it gets smaller. The same thing happens through here. Yeah, exactly. The cross-section gets larger, and then it gets smaller again. And the maximum cross-section is here.
Is there some reason why you didn't cut through the fourth here in the middle top diagram?
I did not make this diagram. Lenny made this diagram. Yeah. I think to not have too many things. Yeah. But yeah, this is really, these two cuts start on top of each other, right? We start with nothing, and then we introduce two sitting directly on top of each other, and then one moves backwards. Nick?
Yeah, so I just had a question about these non-minimal extremal surfaces.
Yep.
Are they somehow, if I'm considering like entanglement wedges and entanglement wedge cross-sections, is there some theorem that you can prove that the entanglement wedge cross-section can never be a subset of one of these non-minimal extremal surfaces?
That would give you intersecting extremal surfaces, would it?
No, I'm saying that like take a boundary reduced density matrix and some portion of the left and some portion of the right, and then have the wormhole be like kind of short and fat.
Yeah.
Is it possible that the entanglement wedge, that the minimal cut that separates the left-hand side region from the right-hand side region of the entanglement wedge will be a subset of one of these non-minimal extremal surfaces? Or is it required to always be a subset of the minimal extremal surface?
Yeah, that's a good question. I don't know the answer. I don't know of any argument that it would be required to be a subset of the minimal one. Generally, if the non-minimal ones are a lot bigger, then you'd expect the cross-section would be sort of larger at that point. But
But it could like narrow. Right?
Yeah, I don't have an argument to say that it can't be. Does it have to be a subset of any extremal surface, the entanglement wedge cross-section?
I think so, because I think it has to be locally the minimal version, the minimal surface version of the geodesic thing. So,
Yeah, I know, but I certainly can have geodesics that, if I extended them, do not end up being like a closed geodesic. It's not obvious to me that it, like in simple cases, then symmetry says it has to be, but it's not obvious to me more generally that it would have to
the
be.
reason why I ask is I wonder if we took the tensor network in this schematic picture that you were looking at, and we took it to be the tensor network that like you worked on with Aaron and John.
Yeah.
Like, if as we iterate through the different distillation surfaces, I wonder if there would be like necessarily a kind of a discontinuous jump that happens.
Yeah, I would have thought if you assume our most speculative and optimistic interpretations of everything working out well, and like just being able to anchor on surfaces and then anchor iteratively, then you can get anything. I don't think you'll have a problem there. But it depends. Yeah, it depends what conjectures about entanglement purification you're willing to accept. Yeah.
Any more questions? Let's thank Geoff again.